now we extend the concept of the observed likelihood to multivariate y case. The concept itself is the same, but we need to define p-dimensional delta because we allow for item non-response. Thus, delta I is a p-dimensional with density, joint density, and we now assume that this is has an unknown parameter. And then for each I, we have a observed part and missing part. So we use this kind of notation. Okay. So now the under the IID setup, the observed likelihood is essentially the integration. So for each density, we have a observed component. So this is the observed I oops y observed, and I and delta I is the marginal is the observation. So this is the original joint density, and then we integrate out over the missing part. So this is the marginal density of this guy is this integrating out. Okay. So if there's no missing data in a particular I, then there's nothing to integrate out. Okay, and for the scalar case, we already showed that. So we now introduce the very important concept in handling missing data. The response mechanism is called missing and random. If the mechanism, the priority condition on y does not depends on y only through the observed part. So as long as this mapping provide the same value, then the priority is the same. Okay. So missing and random means that the response mechanism depends on y only through the observed part. So another way of writing it is that if you use Bayes' theorem, so then this one, you can use Bayes, you have this one. But because it depends on only y observed, so it doesn't depend on missing data, y miss. So this guy is cancelled to each other. So that means actually the missing and random is equivalent to obtaining this one. So that's this is a notation for independence, but this is a given. So this is like a conditional independence. So missing and random is y miss and y and delta are conditionally independent given y observed. Okay. So that is the important concept. And then missing complete random means that it doesn't depend on any y. So this is basically purely random, right? So that's a little bit too strong assumption. And missing and random is a kind of a weaker assumption. And not missing and random is very difficult. I mean, this is more realistic but more difficult. So we'll mostly focus on this missing and random assumption, but later in chapter 8 of our book, we'll cover this topic. So we now study theorem 2.4, which was originally proposed by Professor Rubin. So he's like a big guy in missing data. Father of missing data, they say. Anyway, so P delta given y is the joint density of delta given y, and this f theta y is the marginal density of y. And basically, we are more interested in theta, right? So this is the parameter of interest. But in the missing data, we have integration, so it involves a theta. But under some condition, missing and random condition, we can actually factorize. So once you do that, then see log, right? If you take the log, phi is log L1 theta plus log L2 phi. So if you take the differentiation theta, which is the parameter of interest, this part is 0 because it's phi is not dependent theta. So we need to make sure that these two parameters are distinct. So if you do that, then we have only to maximize L1 theta. So that's good news because we do not have to, under missing and random, we do not have to specify the model for the response mechanism. So sometimes we call it ignorable, in the sense that we can actually ignore this part. Okay. So the proof is simple. So note that L observed theta and phi is what? Fy theta p, so f1, f2 delta, so I should have a y given y free dy I miss, right? And under MAR, we have at f2 delta I given y I phi is the same as delta I y I observed. So that means we can write it this way. So that means MAR, we can write it theta f2 delta I given yi observed phi dy I miss, right? So that means you can do something like this. Times given yi obs phi. So that means you have the first one as a depends on theta only, right? And second part is depends on phi only. Okay, so that gives a complete the proof. Okay. The example 2.4 is used to illustrate the observed likelihood and the factorization theorem. So this one, we can call it a likelihood factorization theorem. In this example, the main parameter of interest is the parameter theta. So the parameter of interest is here, theta. Okay. And the we also have a, suppose we have a marginal density y x with the parameter alpha, and then the response mechanism has a phi, okay, parameter phi. And so we have three parameters, and the observed likelihood. So the joint, right? So so the way we construct the observed likelihood is first consider joint density of all the observation. So that is x and y and delta, right? So joint density of x and y of delta is what? Marginal density of x, and then conditional density of y given x, and then conditional density of delta given x and y. So that's the so I use a different subscript, sorry, but that's basically this part. So you have a marginal x, and then conditional y given x, and then another conditional delta given x and y, right? But since delta is either 1 or 0, we can write it this way. And then for delta equal to 1, we just write the joint density. But for delta equal to 0, we need to integrate out over the missing part, which is the y in this case. So that's the way we can compute the density function, joint the observed likelihood function. Okay. And now once you write it out, then you can immediately realize that this guy has nothing to do with this integration, so it can go outside. Okay, so then you can actually write it, factorize, right? So that means you can safely ignore the marginal distribution of x if, sorry, okay, that's right, okay. So it can go outside if x is completely observed, right? So you can that's good. And then now here's another important point. So if phi2 is 0, so what do you mean by phi2 is 0? So this one is 0. That means delta equal given x and y does not depend on y, so that is just this one. That's exactly missing and random. So on the missing and random, so now this guy is 0. So that means this guy has nothing to do with so independent of y, right? So it can go outside again. Then you end up getting, so then what happened? So this guy goes outside. This guy now also goes outside. Then what's left with is just the integration of f1 y given x and theta dy, which is 1 because it's density. So basically delta equal to 0 it's just so this part so becomes a 1, so it goes away. So basically you end up the theta part, so the theta part is only this part, right? And a phi part you have this way. So one important, very important implication is that on the missing and random, the MLE of theta can be obtained by maximizing L1 theta, which is obtained by ignoring the missing part of the data. So basically you have x, right? And you have y. And you are interested in regression. So you are kind of doing a regression of doing regression of y given x, something like that. Okay, and on the missing and random, you can just use the complete case. So complete case and removing this part, the partial observation, is okay. Is actually does not make any loss of efficiency for the regression if the parameter of interest is the regression coefficient and y is subject to missing and random, then no problem. Okay. Now instead of observing instead of y subject to missingness, if x is subject to missingness, then it's a little bit different, because now because x is subject to missingness, the integration is with respect to x. Okay, so then this guy, previously x goes outside the integration, but not anymore. So it cannot really goes outside of the integration. But on the missing and random, so this is a missing and random, right? Because x is subject to missing, so missing and random means that the missingness does not depend on x. So this one goes outside. So it does not depend on x. So this can go outside. Okay. This can go outside. But then what's left is this guy, right? So L1, that is delta equal to 1 f1 yi given xi theta f2 xi alpha times delta I equal to 0 integration of f1 x theta f2 x alpha dx. So that means what? Although we are not interested in the marginal distribution of x, we still need to specify a model for the marginal distribution of x if covariate is missing. Right? That's the difference. Previously, if the y is missing, right? If y is missing, then we can actually ignore. We don't need the marginal distribution, and everything worked very well. But the story is quite different if covariate is subject to missingness. So that finishes the second part of the week 2 lecture. I mean the chapter 2. Thank you.